All right, so today we're going to get into the fun stuff. And this is factorial analysis of variance. I just made up some data. Well, I didn't just make these up. I believe I made up these actual numbers in 1996. But let's say we're doing an experiment on retention interval, the effects of retention interval on memory. This will be a nice, simple experiment to do. Right? People in the lab class can tell you this is not a hard experiment to run. You give people a list of words, you have them recall them a few days later. And, well, what do we have here? We have 5 minutes, 1 hour, and 24 hours. This would be this is actually pretty standard set of retention intervals, and this is percent correct. So 90, 70, 60. You'd probably get something like that. Unless Mike's in one of your subjects and he studies them in advance. Just an in-joke for those of us who did the lab class. So that's fine. That's all very interesting. It's actually not that interesting. Ebbinghaus found this in 1881. You're not going to get a publication out of this. So you do the analysis of variance. You calculate everything, and you conclude that the retention interval affects memory. Okay. Way to go, Captain Science. So you've done that. Everything's wonderful. But there's more than one variable that affects memory, isn't there? Obviously. The memory class isn't just 5 minutes long. So retention interval is one thing, in time between study and test. But what if we did levels of processing? Now, levels of processing is an idea that Craig and Lockhart came up with in '72, and it's the idea that the more deeply you process something, the more semantically you process something, the better your memory is going to be. Okay? So if I ask people to rate the pleasantness of a word on a 1 to 7 scale, they're more likely to remember that word, excuse me, than if I have them count the number of ascending and descending letters. So if it's written in lowercase letters, and the word is, it's 2 S's. The word's assassin. There's one ascender, and that's the I going up above the line. Okay? A P going below is a descender, right? That kind of thing. So if I have to just count, and that's just looking at the physical properties of the word, they don't remember them as well. Right? So let's look at levels of processing, and we probably find something like this, and we do the analysis of variance, and we find that levels of processing affects memory, and again, this would not be earth-shattering whatsoever. Levels of processing affects explicit memory is not a surprising result. Levels of processing shouldn't affect implicit memory, though. Let's see Challis and Broadbeck, 1992, for a rebuttal. Fair enough. Again, not that interesting. It's old results. The question I want to ask you is, what level of retention interval should you do the levels of processing experiment at? 5 minutes, 1 hour, 24 hours? We can even turn that question on its head. What levels of processing should we do the retention interval experiment at? Dude. This is not that deep question. I'm just trying to keep you interested. So, and I think, let's think about it. Really, those are real serious questions one could ask. When we have, many times, in anything behavioral, psychology, really any kind of life science in general, we don't tend to have single variables affecting something. Our theories are based on this and this come together and do this. That's how they work. So why not put them together? And go, the G's, by the way, mean group. Okay? That's all those G's mean. That's just the notation I use. We have different subjects in different groups, 5 minutes, 1 hour, 24 hours, and we cross it with low, medium, and high levels of processing. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Suddenly reminding me of my childhood watching Sesame Street. They never did that either. Like when you guys were kids, they probably didn't have to, at the end when the guy, like the numbers 4, and then they go 4, lemon meringue, pies, and he falls and the pies all hit him. Sesame Street used to be really edgy. Funny, my brother, who learned, of course, a lot, like a lot of kids, to count watching Sesame Street, he counted like he was from an inner city in the United States. He spoke with a sort of standard Ontario accent like I do, but he'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which was awesome. Like when he was like 3, and that went away. He doesn't get like, he's 44 years old now, he doesn't get like that now. So we got low, medium, and high levels of processing. We got 5 minutes, 1 hour, 24 hours, and we got the 9 groups. We've put these two things together now. Right? And I think you could probably all think in 21, 27, you all knew where I was going with this. So there's got to be a model here. There's got to be analysis of variance, obviously. Let's get a model. Look at that one. By the way, I'm sorry that these are alphas and betas. That's what they're called. These are not the same as the alpha for type 1 and beta for type 1 and type 2 are. Okay? Just like you know. X equals mu plus alpha beta plus epsilon. So this is any score, that's X, right? It's always any score. Equals the grand mean. We talked about that ad nauseum, ad infinitum a couple of weeks ago, which is any score. Everybody starts there. Plus the A effect. The A effect just means whatever A is. It could be retention interval in this case. You want to make a retention interval, that's fine. So in general, we call it A. Plus beta, that's the B effect. So that's variable B. Plus the AB interaction. Okay. They really need wider screens in here. The world has moved on from a 4:3 screen resolution. And it's really annoying. And of course, error, or as it says here, ERL. AB interact. EO. Any score equals the grand mean plus the effective A plus the effective B plus the AB interaction plus the error. Okay. We're just breaking things down. The only new thing here is the interaction term. We have 2 variables, so we're going to, of course, have 2 what we call main effects. They're really just like this guy, just like tau. They're really just like, they're treatment effects. And then we have error, we still have that. The only extra thing we have, the only new thing you have to think about here is how A and B come together. Okay? How A and B come together. How they come together over and above the effect of A and B by themselves, but added up. So the added over and above the additive effect of A and B. Questions so far? Okay. You sure? Good. I think you probably all read this idea before. I don't think Cheryl breaks down like that. Yeah. That's fine. That's not what she's teaching. No, you would have seen them. I don't think so. That's not what that course is about. So. But I know she talks about interactions. For sure.
She breaks it down pretty simply.
Well, it's the effective A, the B, the effective B, effect interaction. Yeah. Well, those are the effects you're interested in anyway. Right? Okay. Let's explain this a bit further. So not only can we look at A and B by themselves, so the effective levels of processing, the effective retention interval, and the effective need this overhead projector from 1960 out of my way. What do they think I'm Don Draper? And then there's a madman in here. I got an overhead projector. What's next? A carousel slide thing where we all start smoking? Don't need that bad. That's how we used to do conferences. We had slides. You know why these are called slides in PowerPoint Keynote? Because we used to use actual slides. You couldn't say, oh, you didn't make typos in your slides, because you would actually print things out using one of them expensive laser printers, and then you would give it to a photographer who would take pictures of them. That's how slides used to work. When someone said, oh, you got to change that slide, you go, oh, I've only got a week. I don't think I can get the slide changed in time. People are so lucky. You young people today and your complicated rap music. So, we're not only looking at A and B, we're going to look at how A and B come together or how they interact. Sort of a whole is more than the sum of its parts kind of thing. Okay, let's think about this. If you come, okay, we're going to predict people's income. And we're going to say there's two important variables, and one's going to be IQ. The smarter you are, the more money you make. And one's going to be what socioeconomic status you came from to begin with. Yes, I know there are people that pull them up through their own bootstraps and end up going from, well, there's Barack Obama, there's Bill Clinton. There are people who become the most powerful person in the world, and they grew up poor. There are people like that. But most people that grow up poor kind of stay there. And most people that grow up rich kind of stay there. Right? It's just the way, I didn't say it was fair. I didn't say I liked it. It just is. Right? It's also true that smart people do better in life than dumb people. Is it fair? No. Life isn't fair. Okay. So, being smart, you make more money. Being rich already, you're going to make more money. Being smart and rich, you're going to do really well. Being dumb and poor, it's got to be worse than just being dumb and just being poor added together. Right? Being black is harder than being white. Right? It just is. Racism, people discriminate against you. It's not fair. I don't like it. It's wrong. It's also true. No, there is no more racism. Obama's president. Being a woman is harder than being a guy. Right? It just is. Women make less money than men. I didn't say it was fair, but it's true. Being a black woman must be even harder than just being a woman just being black added together. That's kind of sad. I can only ever think of sad examples for interactions. I don't know why. Oh, here's one. Drinking alcohol affects your reaction time. Makes it longer. So does taking phenobarbital. Drinking alcohol and taking phenobarbital makes your reaction time really long. Longer than just the phenobarbital or just the alcohol. In fact, if you do it the right way, it'll make it forever because it'll kill you. That's a long reaction time. That's an interaction. Again, I can't think of happy ones, but if you did it right, you'd have a really good, you'd be really wasted.
How about happy kid with a lollipop? Makes me happier kid.
Happy kid with lollipop. Okay, let's go with that. Sure, fair enough. But then you have to go the other way. There's still the sad kid that gets no lollipop.
Or has it taken away.
Yeah, that's right. That's right. Then there's the elephant in the room here. I'm a white male. As Louis C.K. says, doesn't matter what time in history you show up, white people kind of screwing everybody else around, and it's really okay to be a white man. That's a joke, by the way, for those who are scoring at home. He's a comedian. Interactions are basically the whole is more than some of its parts. The idea, right? It's not just the effect of one thing and another put together, added together. It's then there's something else added on. Being a child who Sophie makes sad and steals their lollipop, that kind of thing. Because she does that. That's what her honors thesis is going to be next year. She asked me. She said, "Can I take lollipops from random children?" And I said, "We're going to have trouble getting that through ethics, but and if you want to be mean, that's fine." No, we're not getting. No, we're just going to say that happens in real life. That happens as there's no expectation of privacy. Kids with lollipops have stolen all the time. See what happens. Who's talking about? That's impressive. Because that's when you start thinking you hope you've never read the Birds. It's like, I quit, you know. And that's when someone tells you later on that seagulls really are dinosaurs, right? Because then the dinosaurs, see, a dinosaur stole my chocolate bar, and that is awesome. So now it becomes a great story.
They're down by Bellevue Park.
Yeah.
We decided to sit on the back hatch of the truck.
Right.
And
They steal.
seagulls just came diving at us.
Yeah. That's what they'll
Literally
do.
went down to my daughter's plate, took her burger off, and I was okay, we're inside the truck now.
Yeah.
Because they're diving at us.
Oh yeah. Wait, was it in the spring?
No, it was summertime.
Oh, that's interesting. In the spring, that wouldn't surprise me. That's not uncommon for gull behavior in the spring. You should take animal behavior next year, learn all about it. So while this is depressing, and we're taking lollipops from children, we're causing racism and sexism. We're having dinosaurs steal food from children. We're basically taking things from children. No matter what, I think hopefully you see the point of what an interaction is. And here's a way to put it into words rather than talking about stealing lollipops or racism. The effect of one variable changes depending upon the level of some second variable. The effect of one variable changes depending upon the level of some second variable. If we were to look at, those of you guys that have taken memory or the guys in here that are in the lab class know about this a little bit. If we have retention interval, let's go with 5 minutes, 1 hour, and 7 days. And we have two kinds of memory. One of them is implicit memory, filling in blanks, word breakers. That doesn't decay over time. And recalling the words does. Untitled Chapter and Stark, 1982. Look at this. We have one thing here where there's no effect at all. This is an implicit memory task. The effect of retention interval doesn't even happen. And with the explicit task, it happens a lot. This is all we're interested in here is the interaction. What we care about. It's all we care. The effect of one variable changes depending upon the level of some second variable. That's what an interaction is. Questions so far? So the effect of one variable changes depending upon the level of some second variable. Okay. Okay, so here's a graph. I don't know what we're measuring here. But we have two variables, A, which has two levels, A1 and A2, and B, which has two levels, B1, which is sort of purpley color, and B2, which is kind of reddish. These projectors suck. It looks great on my screen. Isabel just bought a new projector. It's this big, and it's better than any projector we have in this whole university. And it's this big. We got these big pigs. It's horrible. Anyway. And it's brighter. I'm thinking of bringing it camping. Not that Dave talks. Hook it up to the computer, a couple of speakers, you got TV. It rains. That was raining. It's raining. Go inside the trailer watching the TV. So, if you take a look at this, that's exactly what I'm talking about here. The effect of, take a look at the effect of B. B1 is smaller than B2 at A1, isn't it? Right? B1 is a lot smaller than B2 at A2. Right? The effect of B changes depending upon the level of A. Okay. What? There sure is an interaction. The effect of B is big here, and it's small here. It's small at A1 and big at A2. Here's a sort of a little tip. If you have to to talk about the other variable when you talk, if you have to talk about both variables at the same time, you can't talk about one separately, you have an interaction. I can't talk about the effect of B without mentioning A. It's hard for me to. I can say that B1 is bigger, sorry, B2 is bigger than B1. Yeah, B2 is bigger than B1. I can say that, but I have to qualify that by saying, especially at A2. Right? So if I have to qualify that, if I have to mention the level of the other variable, I've got an interaction. Okay? Again, questions? And I know you've all seen graphs like this before. The difference between B1 and B2 is smaller at A2. Oh, sorry, it should say at A1 than it is at A2. It says at A2 than it is at A2. That's just confusing. At A1 than it is at A2. Sorry about that. The effect of B changes depending upon the level of A. It's small at A1 and big at A2. Right? It's small at A1 and big at A2. Do you see that? Does that make some sense? Just look at the graph. It should hopefully fall in place. All right. So far you're okay. So here's the model, x equals mu plus alpha plus beta plus alpha beta plus epsilon. This model has some assumptions. Let's get that out of the way. Let's get the assumptions out of the way and get back to looking at this stuff. So the assumptions of the model itself are that the sum of the alpha sub I is equals 0. So what does that mean? Well, it's just like here. Oh, it's gone. I used to have up there x equals mu plus tau plus epsilon. Remember, if one set of scores went up 2, the other set of scores went down by 2 if we had two groups. So if we were to add the effect of A at level 1, A at level 2 up, and A at level 3 up, that should sum to 0. And in fact, it has to. So if it's going to increase the scores in one group, you get two groups. And let's just make it the ultimate simple kind of design. We can call it 2 by 2. So if we have a 2 by 2, let me just try this up here. And it would look like this: A1, A2, A1, A2. The effect of getting level 1 of A, let's say that raises you up by 2. That means the effect of getting level 2 of A depresses you by 2. Okay? It must. Later on, perhaps today, perhaps Thursday, when we go further into this, you will see that it must. There is no way it cannot. So the sum of the alpha i's, this is just levels. So A1, A2. That's just an index, okay? With the sum of the alpha i's equals 0. The sum of the beta j's equals 0. J is a different index, again, for group 1, group 2. So again, if we were doing it with b's here, let's say B1 raises you by 4, B2 has to depress the scores by 4. This is an assumption of the model. It must work that way. You will see again, as I said, that it does. And there is no way it cannot. Okay. Questions so far? Good? Okay. The sum of the alpha I beta j's, there should be a j in there, alpha I beta j's equals 0. Now what does that mean? That means the interaction terms must sum to 0. So, if this one here raises your score by 3, A1, B1, that must depress your score by 3, that must depress your score by 3, and this must raise your score by 3. So if A1, B1 is plus 3, A2, B1 must be minus 3, A1, B2 must be minus 3, and A2, B2 must be plus 3, because they have to sum to 0 altogether, but they also have to sum in rows and columns to 0. Okay? Questions so far? Even if you don't understand why yet, you understand what I mean when I say that. Okay, good, because we'll get to why, and it will act. If you understand why already, that's great. If you don't worry about it. We'll get there, and it'll make all complete sense. Okay, this is just a standard assumption. Error is normally distributed and independent, NID, with a mean of 0 and a sigma, and a variance of sigma squared. In other words, the error is normal and random and independent. That's a standard assumption in analysis of variance. Shouldn't surprise you. We need a wider screen and a projector that points higher up, so it's not just like a pony in the way. The ergonomic genius designed this room. Yeah.
What did you say that meant?
Error is normally distributed as the n, independent, with a mean of 0 and a variance of sigma squared. So what all it means is that the independence part just says that if I know the effect of being u, I don't know the effect of being her. It's never the independence assumption I was talking about, right? So that's all that really is. The fact that it's going to have a mean of 0 just means that if we add all the effects of all the people up over and above the grand mean, it'll just sum to 0. So it's another sum to 0 one, but it's also saying it has a variance of sigma squared and epsilon, which is error variance. We have to give it a name, so we call it sigma squared and epsilon. Other questions? Good question. Is this good? Okay? Yeah, yes, you're okay right now. Just sure. You sure? I've been back here before a lot, so I'm just checking out who's okay back here. Yeah, you can actually see from here. Okay, it's not that. That's a good seat. This is why Mike's got a good seat. I think Sophie's probably the worst seat. No, the worst seat's right here.
That's the worst seat right here.
No, here. This is no. Believe me, Benny, you sat there. You can't see anything.
I tried at the beginning.
Because look, usually I'm standing here, plus this whole monstrosity is in the way. Right. Yeah, I don't know. This is horrible. We got to do something. I've got to talk to that committee. See, that's my job. You don't understand the other parts of my job, the parts I hate. Well, now I've got to talk to a committee. Anyway, sorry, I'm back. A horrible meeting on Friday, except that then the way I'm going to get through the University Senate meeting on Friday, those of you that follow me on Facebook know how much I love University Senate meetings. Through the whole thing, I'm going to sit there thinking, but soon I go to Florida.
Yeah.
That's all I'm going to think as I'm seething with anger. Okay, so that's the model. The F, we're going to have to do some F tests. It's analysis of variance. You got to do the F. And I don't mean the delicious Vietnamese noodle dish. Nobody? I mean F test. It's got assumptions as well. Homogeneity of variance, which you know. Random samples. Okay, we can violate homogeneity of variance kind of severely, about 4 to 1. Told you that before. We can violate the crap out of a random sample. Happily, because most of us don't have the resources to do true random samples. Right? Then all research will be done simply by big polling companies, like that do election polling, and that would be horrible. We don't need random samples. We don't need those thinking random samples, man. All we need really are some people, or some rats, or whatever. It's nice. ANOVA really stands up well to violations of the random sample assumption. We need normal populations. Again, we can violate the crap out of that. And technically it needs it, but we don't really need it. So technically, random sample, normal population, we don't really need those things though. They're just nice to have. If you get those, it's even better. The nice, you know what, when you violate an assumption, it makes the test more conservative anyway. So that's the nice thing. It doesn't give you false positives when you violate an assumption. It gives you false negatives. So the nice thing is you don't make an idiot of yourself saying something happened and wasn't there. It's just that if something's there, you might miss it. And that's no good. You violate those two all the time. Any experiment ever that tests if men and women are different. Well, being male or female are not normally distributed. Just aren't. Right? It's binary. And don't go into all this stuff about, well, it's just a continuum. I'm talking about number of Y chromosomes one has. Yes, I know there are people with more than one Y chromosome. I'm not stupid. I'm annoying, sure. Bit of a know-it-all, but I'm not stupid. I'm actually a professional know-it-all. Okay. Okay, here's a numerical example, which is only half on the screen. That's just fracking dandy. Okay. You know what? You bring tape? You just tape that right on there. That works.
Why don't you just pull it up and you can see it on the phone?
What do you guys think of that? Would that be better? Is that better or is that worse? Like, I don't know. I can't see, eh? So I don't know if that's better or worse. Like, to me, it doesn't look really a whole lot different.
Colored in with white chalk.
Well, no! Okay, why don't you do that, Nigel? I think this is worse. I mean, I think it's a matter of, they're both pretty bad. But if, look, what's going on here is we got A1, B1 has 9. These are group means. I'm just making up means. B1, A2 is 7. A1, B2 is 3. And A2, B2, which is a really lame version of a robot, is 1. Worst R2 unit ever. It's the beta version. What do you guys think of the whole thing with this new Star Wars things? You think it's good? No, there's going to be a whole bunch of new Star Wars stuff. I wonder if they'll. Well, I've always with that. I would ask, are they going to start getting good? Star Wars just isn't. Star Trek, that's good.
I love the first Star Wars.
Yeah.
The first original one, yeah. But then they kind of went over.
No, I think the second one's a great movie. The third one's even good. And then those 3 prequels were horrid.
One time Yoda tweeted at me.
What's that? Who did Yoda? Yeah, it's not really Yoda. You know that.
No, it
Yoda's on Twitter. That's great. That's great. That's good. That's good. Okay. Frank Underwood from House of Cards follows me.
Oh.
Yeah. So. Yeah. I don't know what it is. J.J. Abrams apparently is going to have something to do with it. So. But Star Trek is more important. Much more important. Okay. So there we go. There's an I don't know. Look, I don't know what A and B are. I am not a creative person. I don't do that stuff. I can make up experiments, but they're, look, it's A and B. They have 2 levels, 1 and 2. Make up your own variables. Okay. We know this, x equals mu plus alpha plus beta plus epsilon. And I can do it for 3. X equals mu plus alpha plus beta plus gamma plus alpha beta plus beta gamma plus alpha gamma plus alpha beta gamma plus epsilon. It's easy. You do this enough, it just sort of memory burn. Okay. What we're going to do is we're going to take out parts. We're going to break these numbers down into their constituent parts. Okay? That's what we're going to do. We're going to break it down into their constituent parts. And it's kind of cool. And in fact, in essence, that's what analysis of variance does, right? We partition everything. The first thing I'm going to do is I'm going to take out the grand mean, and it applies to everybody. So the grand mean here is going to be, well, 9 and 7 is 16, and 3 is 19, and 1 is 20. So the total is 20. I'm now going to divide by 4 because there's 4 cells, 4 groups. And when they're mathematically inclined out there, 20 divided by 4 is 5. So the grand mean is 5. Okay? Everybody see how I got that? You see how I just took the numbers, added them up, and I'm dividing them by 4 to get the grand mean. Does that make sense? You good? Okay. So now I'm going to take 5. I've taken 5 out of each cell. I'm going to remove the grand mean. And that's what I've done here. So with the grand mean removed, we can now go on and see if there's any effect in A and B. Well, I took the grand mean out, and you end up with 4, 2, negative 2, and negative 4 for A1, B1, A2, B1, A1, B2, and A2, B2. Now what I'm going to do now is I want to find the effect of B. So what I've done here is I'm summing across A. 4, 2 is 6, negative 2, negative 4 is negative 6. I'm now going to divide by 2, because for B1, I have 2 things. I'm just taking the average elevation of scores in B is plus 3. It scores up by 3. We know that it must decrease the scores by 3 in B2, because that's an assumption, and in fact, that's true. It's negative 6 divided by 2, which is negative 3. So the effect of B1, so the simple main effect, we would call that of B1, is 3, and the simple main effect of B2 is negative. Do you see how I got that? Makes sense? Everybody's good? Okay. So again, all I did is I summed across A. I'm ignoring A. I'm just getting the effect of B. B is different at level 1 and level 2. Unlike the grand mean that applies to every single cell, this one here only applies to B1. This one here only applies to B2. Okay. I'm now going to suck that in. I'm removing 3 from B1, and I'm subtracting negative 3 from B2. Now, subtracting negative 3 is the same as adding 3, for those of you that forgot about that. Right? So now what I have, now I've removed, actually, just out of curiosity, if you take a look at this, if I've removed the grand mean, if I've subtracted it, this thing holds, oh look, it all sums to 0. If I've taken out the effect of B, if I go across B, oh look, it sums to 0. See, they're gone. They're gone. It's magic. It's not at all like magic. It's like I'm David Copperfield. Who was he married to a long time ago? Carmen Electra or something like that? Because I always figured his biggest magic trick was convincing her that he was attractive. Thank you. Not really my joke. Don't know whose it is, but I stole it from somebody. Okay. So now let's go across, sum across B will be effective A. 1 and 1 is 2. I always hope that whenever I get to this slide, nobody from the math department's walking by. Yeah. 1 and 1 is 2. And negative 1 and negative 1 is negative 2. So the effect of A1 is 1 and A2 is negative 1. Again, note that they sum to 0. Note, yeah, go ahead. You'd always start with the thing that's the most, to make it easiest, it's sort of this most general, so the grand mean. You actually could do B first, then A, then the grand mean, then the interaction. Yeah. It's a lot easier to make mistakes that way. Oh yeah, sure. So if you had like A, B1, B2, B3, so you just go across for all 3 B's, and maybe it's plus 3, minus 2, minus 1. Right? It just only sums to 0 altogether. Yep, good question.
Do you ever have to fix it for the sum to 0?
Pardon me?
Do you ever have to
No, if it doesn't sum to 0, you made a mistake. It can't not sum to 0. It just must. You could make up any. The only reason that these all come out as whole, the only way that these are fixed up so that they work, is that I want all whole numbers and no fractions. This makes life easier. But if you give me you can give me a 10 by 15, you give me any set of numbers, it will sum to 0. That's just the way the universe works. It can't not work that way. Because what we're doing is we're taking deviations from a mean out, right? And deviations from a mean must sum to 0. We talked about way early, right? That's all these are deviations from the mean. The mean's been removed, so all that's left are deviations from it. Right? So it has to balance it, and so therefore it must sum to 0. So if you ever were playing with one of these and they didn't sum to 0, you made a mistake. You must have made a mistake. There is no way you can't have made a mistake if they don't sum to 0. So, well, the same thing we did before, we'll do it for the A's now. We're going to take out 1 from all the A1s, and we're going to take -1 from all the A2s. And we're left with a whole bunch of zeros. So there's nothing there. So there's no interaction. The last thing left would be A and B, and there's no ABs. They're all zeros. There's nothing extra after the min X. Right? So the only thing you have left are zeros. All you have left are zeros. So there's no interaction. You okay, Amanda?
How would you have 0 left if you minus 2?
No, you subtracted 1.
Why would you subtract 1 if it's to 2?
Because you divide by 2, because it's an average. Right? No, think about it. Look at the page. It sums. It's just an average. Remember before with the grand mean? Remember it summed to 20. We divided by 4 because there's 4 observations. Well, here this sums to 2. We divide by 2 because there's B1 and B2 level of A1, let's say. Right?
Is that what we did with B2?
Yep. Remember, it summed to 6 and -6. We divided by 2 to get 3 and -3. Why did we divide by 2? Because it's just an average. Yep. Good. Glad you asked the question because it's easy to get tripped up. It's better to ask than not ask. So no, it's not like I'm doing something tricky. Right? They're just averages. They're just averages. And if we had 3, right? You asked if we had 3, what would happen? Well, we would add them all up and divide by 3. Right? Because it's just an average. All we're doing is getting averages.
So if you have 2 levels of one variable and 3 levels of another variable,
Yeah.
everything will still equal out to 0.
It has to sum to 0. It must sum to 0. Yes. And it will. It can't not. Unless you make a mechanical error.
So how do you know there's an effect then? With something if it's all averaging out to 0?
Well, it doesn't
There would be
add.
no effect
Look.
of anything.
Well, what if we graphed this and saw the actual numbers? Don't you see effects there? Yeah, right? So, I mean, look at that. What do we have there? B1 is bigger than B2. We actually had numbers at B1 and B2, didn't we? +3 and -3. And A2 is smaller than A1, isn't it? On average, there, roughly there. The scores at A2 are smaller than the scores at A1. Now, do we have an interaction? Well, we know, first of all, just by playing around with it, we don't. But look at that right there. Does that look like an interaction to you? Well, no. The effect of A, well, it's probably easier with this graph to look at the effect of B. The effect of B is this size here, and the same size at A2. There's no interaction. Right? The effect of A doesn't change depending upon the level of B. It's the same. They're exactly the same. Okay. Let us do another one. For then it was proclaimed that they will do another example. And on that day, I don't know, something with magic. I don't know. And then things with cloven hooves and horns and such. And then the shaman came from the hills, and he played his horn. Do another example, he said. So they did. Okay, here we go. A1, A2, B1, B2. Again, I don't even know what these A's and B's are. They're A's and B's. I just don't. But here's some scores. 20, 0, negative 10, and 2. I sound way more excited about that than I should be. What are we going to do? First, we are going to remove the grand mean, because the grand mean applies to everything. It's easiest to start there. We're going to do 20 plus 0, there's a hard one, minus 10 plus 2 divided by 4. That's going to give us 3, because it's 12 divided by 4 is 3. Please, go ahead. Yeah.
You divide by 4 twice. Well,
97 is 16 plus 3 plus 1, so that's 20.
yeah.
Divided by 4 is 5.
Oh, you just wrote it out.
Yeah, okay.
Never mind.
That's okay. That's okay. No, I've taught these examples. Four times. Six. 19 times. So, yeah. No, typically I wouldn't. Oh, really? Have I? No, I didn't. Yeah, I know the examples. Okay, so we're going to take out 3 from each of these. So let's remove the grand mean. Now let's take a look. 20 minus 3 should give us 17. 0 minus 3 should give us negative 3. Negative 10 minus 3 should give us negative 13. 2 minus 3 should give us negative 1. Okay, now let's just see if I can do arithmetic in my head. Why, yes, I can. So, the grand mean's gone. I don't know, this time, just to be different, just to change it up, you know, to a little spice. I'm going to do the A's first, not the B's. Okay. 17 plus negative 13 is 4. Negative 3 plus negative 1 is 4. Negative 4, we're going to divide by 2 because we have 2 observations. Okay? The A effect is 2 for A1 and negative 2 for A2. By the way, you can convince yourself that you've removed the grand mean properly because already all these things, now that the grand mean's gone, this should be what? 0. Now should be the mean, right? Oh, look, it is. Cool. You can always check your work all the way through whenever you're working on one of these things. The beauty of it. So we got 2 for A1 and negative 2 for A2. So let's remove those. Note again, they sum to 0. This is not magic. It is a property of how numbers work. This isn't me cooking up an example so it worked that way. The only way it's cooked up is such that I don't want to use fractions because you could end up with a quarter doing the grand mean. Yeah, did it?
When you're doing your columns, you're adding, but when you're doing your rows, you're subtracting.
No. You always add. Always add. Say divide by whatever number of observations. Yeah, there's nothing tricky like that. Except on Tuesday. No, I'm kidding. Yeah, so you just add them, right? Just take a look. See, always add them up, divide by 2, divide by 2. Add them up, divide by 2, divide by 2. Yep. Nothing tricky. Don't look for, the world wouldn't be that complicated. I would quit if it was that like that. That'd be like a Twilight Zone episode. You mean you have to subtract now? What? Something's wrong. You're entering a world of light and sound and statistics. It is the analysis of variance zone. Submitted for your approval. I'm doing a guy that none of you have ever seen. He died before I was born. Well, I was 5. Take 2 from A1 and negative 2 from A2. I did that. You can always convince yourself, oh, what? Well, that sums to 0. That's good. The A's sum to 0 now. Let's take a look here. 15 minus 1 is 14, and negative 15 plus 1 is negative 14. It's going to be 7 and negative 7. I don't know what that extra A is there for. I don't know what that's doing there. But like I just said, notice that the cells sum to 0. The grand mean's gone. And so do the columns, because we've taken out Oh, no, that makes sense. We've taken out A, yeah. But that should be, oh, there's a space there. Damn you, variable width fonts. But now we'll do the rows, going across. 15 minus 1 is 14, negative 15 plus 1 is negative 14. The only way it sounded like I was subtracting because I was adding a negative number, that's all. That's probably what it was. No, that's probably what it was. It was probably because I just actually said 15 minus 1, and what I'm doing there is I'm saying 15 plus negative 1. So I was probably saying that. That's probably what we're using. So 14 and negative 14, it's going to be 7 and negative 7. Again, divide by 2. So for B, we have B1 is 7 and B2 is negative 7. So well, you should take those out. I've had about enough of B1 and B2. Let's remove them. They've had their time. Look, I got to keep myself interested in this too. Again, I've done it 19 times. I look out there and I just see everybody I've ever taught. Like I see Keo sitting over there and there's Lori. I mean, it's just... Okay. Well, now what's left is going to be the interaction. So this time we have one. We've taken out the grand mean, we've taken out the A effect, the B effect. What's left? Well, there's nothing else left. Now, I want to tell you something. I have not put individual scores in. These are just cell means. We don't have the error effect in this. I can do it this way, but it becomes exceedingly complicated. So I'm just showing you what the analysis variance actually does, how it breaks things down. But I'm not actually taking, these are just cell means. So we have an interaction, 8, negative 8, negative 8, 8. Note the effect sum to 0 in every possible way. It's like the Hollywood squares. This way, well, not quite like the Hollywood squares because it doesn't work diagonally. It doesn't have to. They all together sum to 0. They sum to get to 0 in rows and columns. If it was just zeros, we'd have no interaction. But they aren't zeros, they're non-zero. But they still sum to 0. So that means being at A1, B1, not only do you have an effective A and an effective B, but also it adds 8 more to your score. So we have an interaction here. But it, like everything else, always sums to 0. Oh, yeah, sorry. Or you're just doing that with your hair or something? No? Yeah? Or whatever the hell that is, I can't see from here. For all I know is you're just getting ready to shoot me. No idea. Yeah, you're just aiming down the barrel. That's it, I've had enough, brought back. And you know what you say at the end after you, screw you, brought back. If we graph this thing, it looks like that. So remember last time, this is the one we ended up with, where I graphed it out. And that shows us there's an interaction. One of the interesting things that this graph shows is that while graphing helps, clearly there's an interaction. I mean, if the lines are crossing, the effect of one variable changes depending upon the level of the other variable. That's pretty obvious, right? I mean, first of all, B1's way bigger than B2 and A1, and then, in fact, they're almost equal at A2, but in fact, the order's switched. I should tell you something. It's hard to see where there are effects, though. Like, is A bigger than B? A1 bigger than A2? Is B1 bigger than B2? It's a tough call. Interactions are a lot easier to see typically than main effects, especially when you have these kind of interactions where they cross, which have a special name that I will mention shortly. All right. So when we interpret interactions, so no matter as far as the interpretation part goes, this is, what does this mean? So when you look at your data, what does it mean? You got to be careful talking about main effects in the presence of interaction, right? Because by definition, when you're talking about interaction, you're saying that the effect of one variable changes depending upon the level of a second variable. Is it possible then to talk about a main effect without mentioning the interaction? Because when you talk about main effects, statistically they're there. That's not the issue. It's a question of, is it something you can interpret? With an ordinal interaction, that's one where the order of the main effects is preserved. So that would look like say this. Going on parallel. There's an interaction there. You can see that the effect here is smaller than it is here. But the order of the main effect is preserved, right? So if this is A1, A2, B1, B2, the order of the main effects is preserved. B2 is bigger than B1. But that difference is a little smaller here at A2 than it is at A1. I'd be pretty comfortable personally interpreting that main effect. Because while the effect is smaller at A2 between B2 and B1, it's not like it's something that makes me say, oh, I can't talk about this without mentioning the other variable. Right? I can. I'm perfectly happy doing that. I don't have a problem with it. So it's pretty easy to do, and that's what's called an ordinal interaction. That's when the order of main effects is preserved. When we have a disordinal interaction, it's really almost impossible to interpret main effects. I mean, you could draw something like this. Okay. Well, A1 is bigger than A2 at B1. That's all I can say. I can't say. It's probably the case, in fact, that B1, on average, look, is bigger than B2. Yeah. But do you feel comfortable talking about that? Can you do it without mentioning the other variable? And it becomes very difficult. So typically, one would say, I'm not going to do that. I will report the effect in a paper I'm writing, but I won't interpret it. What I'm going to interpret is the interaction. Right? So if you think about the sort of classic memory example, the 12-inch Chapter and Stark example I gave you the other day, where we have 3 retention intervals, which is 1 hour, 24 hours, and 7 days. And we have an explicit memory test, which is actually an experiment. It was recognition. So it's there, there, there. Looks like that, just like you would expect. And they had an implicit test, which was word fragment completion. And it's there. So this is the implicit test. And this is the explicit test. Just spelled explicit. Okay. Now, in that case, because on average, if you sort of collapsed across memory test type, there's a main effective retention interval. Right? There is. Would you interpret it? Well, no. Because you wouldn't say, well, say statistically, you would say, yeah, I have a significant effective retention interval, but I don't care. Because retention interval only affects explicit tests, not implicit tests. I can't talk about retention interval without mentioning the test type. Right? So in that case, you don't interpret it the main effect at all. It would be silly to. Right? You will hear people say you never interpret an interaction in the presence, a main effect in the presence of interactions. I think that's a little strong. It's a defensible position, but I think it's a little strong because if we got something like this, I'm pretty comfortable talking about that there. I'm pretty happy with that. I wouldn't do it here. That's ridiculous. I wouldn't do it in this one either. Right? So I might say that B1's bigger than B2. I might be happy with that. Yeah. But I wouldn't talk about the main effect of A. It's probably there. Because I can't talk about it without mentioning it. Right? And I probably still wouldn't end up talking about the main effect of B. Unless there was a really good theoretical reason to. So you got to sort of always realize that there's 2 things. There's statistical significance and there's practical significance. Statistically, something can be significant. That's a non-issue. That happens all the time. 0.05, great. But does it mean anything? Right? It's like if you test enough people, you will find differences all the time. You'll find correlations that are significant, for example, between, let's think of something completely inane. There's a correlation, I guarantee you, between the size of your big toe and the number of children you have. Positive. You know why? Because adults have bigger toes than children. Children don't have kids. Is that, and it would be significant too. Does it matter? Probably not. Right? So it's a matter of, do we interpret that or not? And that's the case with some of these things. Statistically, there is, if you go back and read Untitled Chapter and start, statistically there is a significant effect of attention interval. They don't talk about it because it's stupid to. You can't. Because you can't talk about one without mentioning the other, without one variable without mentioning the other. And that, to me, is the test. That's what I do. If I'm writing something up, I read it, I look at the graph, and I say, can I talk about one variable without mentioning the other? If I can, I'll go ahead. If I can't, I just don't. I don't talk. I report it, but I don't interpret it in the discussion section. Right? So it's a matter of, can I, in good faith, talk about an effect of a variable without mentioning any other variable? If I can, then I'll talk about it. Then I'll do that. Make sense? All right. So, remember how we partition the degrees of freedom and sums of squares for the regular analysis of variance, for the sort of one way, the vanilla one, I guess you might want to call it. Well, let's do it with this for the two-way analysis of variance. Factorial. Okay, so remember our model, which is x equals mu plus alpha plus beta plus alpha, beta plus epsilon. Right? And that's going to tell us what our sums of squares are going to be. We're going to get a sum of squares for A, we're going to get one for B, we're going to get a sum of squares AB, and we're going to get a sum of squares error. And those should all add up to a sum of squares total. Okay? Okay. Questions so far? Okay, good. So sum of squares total equals sum of squares A plus sum of squares B plus sum of squares AB plus sum of squares error. And then those will have degrees of freedom to go with them, and we'll partition them along with the sums of squares. Okay. Questions? Make sense? It's the same thing we did before with one-way ANOVA. Yeah, please.
In the factorial equation, is
Yeah.
it possible to just switch mu with x sub g, meaning grand mu?
Yeah. I mean, like, what you mean in the model?
Yeah.
No,
Why?
because those are parameters. They're not statistics. Using x bar sub g, that an x bar is a statistic, not a parameter.
Oh.
That's a parameter. The model is parametric. It's about populations. The statistics, which is how we actually end up doing this, different matter. But that's in essence what you're doing. What you're saying technically is incorrect. You can't do it, but practically you're right. Practically you're right, because in fact, when we start to break this thing down into these great big sum of this minus this, sum of this minus this, in fact, we talk about grand mean, we'll talk about x bar sub g. But so practically you're right, but theoretically you can't in the model itself, because the model is about parameters. It's not about statistics. But the parameters, the way the parameters, I don't want to use the word interact, the way the parameters work together in the model, that's what tells us how the stats are going to work. Yeah, it's a good question. A very deep question, actually. All right. Other questions? Okay. So think of it this way. We got sum of squares for A. That's just the same, and a sum of squares for B. Those are just going to be square deviations of column means from the grand mean. So columns and rows. It's the same thing we did before with the deviations of group means from the grand mean. But now it's going to be columns, so we're going to put A in columns, which I tend to do, I think, and B in rows. Right? So if I was to sort of draw this, diagram this out, And there's groups in here. So if we're getting the sums of squares for A, we're going to get this, the column mean. Right? So this is going to be the x bar for this column, and then the x bar for this column, and then we're going to those deviations from the grand mean. For B, it's going to be squared deviations of the row means from the grand mean. So we're going to get these row means from the grand mean. So we're ignoring, if we're getting the column means, B's, we're ignoring the levels of A if we get the row means. Right? We sum across them, divide by, in this case, 2. Just like we did when we were breaking down the tables the other day. Right? That was what we were doing. Remember that? We'd add them up and divide by the number of observations, which, because I was making them simple, was always 2. Okay. Questions? Now, so keep thinking about this. This is the harder one, sum of squares AB. These are square deviations of cell means. That's the cell means, the individual values in here. The cell means, the averages for there. Because remember, when we did that, I said those were cell means. Those are averages of scores that people got. So the square deviations of the cell means from what we would expect given the row and column means. So put the row and column means in, and do we get anything different from that? Because that's what an interaction is. Is it different from what just affect the contribution of A and the contribution of B? In other words, again, thinking back, when we broke those things down, we're going to get what's left over. We take out the row, we take out the column, take out the grand mean, right? What's left is the interaction. Those are deviations. In that case, they're deviations from 0 because we took out the grand mean. So in fact, if you squared those numbers and summed them, you get the sums of squares for interaction. So if it's like, plus 2, minus 2, minus 2, plus 2, okay? The sums of squares for interaction would be 16. 4, 4, 4, 4. If the column means were plus 5, minus 5, the sum of squares for A is 50. 25 and 25, 5 squared twice. If it's plus 7 and minus 7, the sum of squares for B is going to be 98. 49, 49. That's what. See, there was a reason I was having you do all that stuff with breaking down the tables and showing you take out this and take out that, because that's actually how it works. We took out the grand mean to just purely have the main effect there. So they're just deviations from 0 instead of deviations from the grand mean. Right. Questions? Sum of squares error, that's really the easiest one. All those are square deviations from individual scores from their cell means. The scores, the average for A1, B1, whatever the hell it is, let's say it's 9, and there's 5 people in that group, well, so there's numbers like 8, 12, 9, 11, and 10. That averaged to 9. No, one of those should have been 7. Anyway, we take those deviations from their cell mean, we square them, do that for that cell, then we do it for this cell. And we add all those up, then we do it for this cell, add all those up, and do it for this cell, and we get the sum of squares for error. We didn't do that when we were breaking out tables because it's a pain. principle's exactly the same.
What's this all mean again?
What's the cell mean? It's just like what the average is for A1, B1. What's the average score in A1, B1? What's the average score in A2, B1? Right? So, oh, I almost hurt myself there. So if like this was 5 in here, A1, B1, that's the cell mean. So then you do deviations of individual scores, the individual subject scores, from that cell mean.
Then do you combine all cells?
Yeah, you add them all up, add the deviations up, yes. Add the square deviations up, and then the next question.
No,
Okay?
that's okay. I think I got my own answer.
You think you're okay? Okay. Is this making
I
sense?
think of that.
See, we didn't have that in there because those would have taken forever to do those examples. Because then I'd have to do all the, it's just a pain. But if we had 5 scores and their average was 9, right? So we have a score of say 9, and 10, and 8, and 7, and 11. We take all those scores and how much they deviate. The sum of scores for error, the contribution from the one cell in that case would be 10, because we get 2 and minus 2 and 1 and minus 1 and 0. Square all those things, add them up, and that gives you 10. They're just deviations of individual scores from cell means. The same way we had deviations of individual scores from group means for sum of squares error, and we added them up to the next group for one-way analysis of variance. It's exactly the same principle. It's literally exactly the same principle. And I'm using literally properly there. Not the way so many people use it, where they mean figuratively. Which drives me crazy. No, this is literally apples and oranges. No, it isn't. Literally apples and oranges is literally apples and oranges. I see no fruit here at all. It drives me nuts when people do that. It's really simple. English is a subtle, wonderful language, and it's really easy to make mistakes, but it's also easy to speak properly if you have a vocabulary and know the grammar. But irregardless, so that's just lazy. It's actually a word, but it's lazy speaking. Okay, now I'm going to show you the math. Don't get worried. Don't get worried. Don't get worried. Okay. No, all this is, guys, all this is what I was just saying. All this is what I was just saying. Take a look at the one on the left. That's for sum of squares total. It's individual scores minus the grand mean squared. There you go, man. Great. These are being weighted by the number of groups, number of levels. So if that's A, it would be 2, and B, that would be 2. N is the number of subjects per group. Okay? Don't worry about the weighting so much right now. Take a look at what's inside the brackets. Okay. X bar sub j, that's going to be the column means. And then there's a dot there, and that means I summed across, I ignored the b's. That's all that means. Just notation. Minus the grand mean squared. Column means, wherever column means, minus the grand mean squared. Just what I said. This is all that this stuff is a way to write stuff out and not have to say this in all these words. This is the interaction. This is each score. Okay? And we subtract the cell mean. We subtract, screwed that. We subtract this is individual score, subtract the row mean, the column mean, and add the grand mean back in. You're going, what? Why are you adding the grand mean back in? Because if you take out the row mean and the column mean, right? The row mean and the column means together make up the grand mean, don't they? So if you take it out twice, what you've done there is you actually removed the grand mean twice, you got to put it back in once and balance everything back out. All that is taking the cell means and subtracting what you'd expect. And then finally, this is the one that you can't see.
There we go.
Okay. Okay. Yeah, sorry, this is the sum of scores for error. Individual score minus the row mean, minus the column mean, plus the grand mean. This is the column, the cell mean minus the grand mean squared. Why is this summed a whole bunch of times? Because you got to do it once here, once here, once here, once here. Every time you do this, you got to sum it. This isn't something to worry about. The point of this is, it's exactly what we did when we took stuff out. Remember we were taking things out and then getting numbers? That's just mathematically saying, remove the grand mean, and what score do you have? Remove, for A, what scores do you have for B? What deviation? What do you have left over? That's all that is. So, the whole thing has big N minus 1 degrees of freedom. Big N is the number of observations. That shouldn't surprise you. How many values have you fixed here? Remember, we're doing degrees of freedom. How many values have you fixed? No. To do this, just one. And you're going to say, wait a second, you calculated that. And you say, no, the numbers don't know where they came from. You're fixing one mean. You have, how many levels of A do you have? Let's say we have A levels of A. So we lose A minus 1 degrees of freedom. This is just like how we have K minus 1 degrees of freedom. Right? K minus 1 degrees of freedom. For number of groups, minus 1. This is number of levels of A. So, coincidentally, for B, it'll be the number of levels of B minus 1. Now think about this. If we were breaking this down, and I said to you, or instead of breaking it down, let's build it back up like we did in the quiz, right? Okay, what's the effect of B going to be? For B1, what is it? Give me a number. 6. So it's going to be 6 for... What happens to B? Oh, it's got to be minus 6. It must be. They must sum to 0. Remember that? So you've lost 1 degree of freedom. You have 2 minus 1, which is 1. For the interaction, you have A minus 1 times B minus 1. How in the hell? What? Well, think about this. Take a look. So let's say we have a 2 by 2. So the interaction, let's put a 6 here. Oh, minus 6, plus 6. Okay, we have 1 degree of freedom. We were allowed to put 1 arbitrarily. Okay, let's put a 4 here. I don't know, we can do something else. Put a 2 here. Yeah. Uh-oh, 4 minus 4. It's going to be minus 2 plus, so that's going to be minus 2 again, and then that means that's got to be plus 2. I had 2 degrees of freedom. I put 2 values in arbitrarily, and 2 times 1 is 2. Let's make it bigger. Let's make it a 3 by 3. So let's just use ones. Makes life a little easier. Put a 1 here. Let's put a 1 there. Put another 1 here. Put a 1 here. So that's so far 4. I've been able to just put up whatever I want. Oh, but that's got to be minus 2. It must be, right? Because that's got to sum to 0. Oh, now that's there. So that's got to be plus 1. Doesn't it? Has to be. Minus 2, that's got to be minus 2 here, which means that's got to be plus 1, that's got to be minus 2. Notice how it all sums to 0. Right? So I have 4 degrees of freedom there. 3 by 3, 3 minus 2 times 3 minus 2. Sorry, 2 minus 1 times 3 minus 1. 2 times 2 is 4. If you have a 9 by 9, you have 64 degrees of freedom. I'm not going to do one of those. It'll take a long time. If you have an 11 by 11, you've got 100 degrees of freedom. Right? 11 minus 1 is 10. 11 minus 1 is 10. 10 times 10 is 100. All right. Questions?
Is it not just helpful to think of this like Sudoku, but everything has to equal 0?
If you like doing that stuff, I guess, yeah.
And what is the P and the Q?
The P and the Q are the number of levels of A and levels of B.
So which one? Oh, right, I is the
What do you mean by levels?
1, 2, 3. 3 levels. Levels of the variable. Completely carved. Like ancient Egypt.
High, medium, low.
No,
I was just saying like high, medium, low, or.
high, medium, low,
sad.
0.57 drinks, if it's an alcohol experiment. Yeah, high, medium, low is great, sure. There's a number of levels of the variable. Perfect. Yes, Sophie?
A minus 1 and B minus 1, is that for these?
Levels of A.
Air?
No. That's the number of levels of A, levels of B. This is
That's
for the,
for the air?
that's, no, sorry, I screwed that up. That's the interaction.
Okay.
For the error, this is wacky. How are we going to do this? Error is interesting because we're doing deviations from each cell mean. How many subjects are there in each cell? No, there's not one. You could do the experiment then. That's just watching stuff happen. That's not an experiment. Right? Single subject design, you know what that is? That's watching things happen and writing some of it down. It's not an experiment. I may have a different view of that than some people, but that doesn't matter. I'm right, they're wrong. No. That may be true, but you know, make up your own mind. Okay, how many subjects, in general, how many subjects are in each cell? Generally. It's not a number, it's a letter. And little n. Little n. When we do the deviations from the mean in the cell, how many degrees of freedom have we lost in each cell? Like just within the cell. 1. How many cells are there? Yeah, so generally what would you say? No, on K, because K is just for, there's K groups. How many, well, yeah, but how many groups are there? So what is K equal if you want to call it? No, you can't just pick another letter. You can't just, yes, A times B. Well done. Right, because there's A times B groups. Excuse me. Toaster strudels for breakfast. Those things, by the way, are horrible, and they're also nature's perfect food at the same time. They come with that little packet of horrible icing. And you can never get it to come out looking like it does on the box, and you try. You know, got up this morning and I said to Jonathan, what do you want for breakfast? He said, he does, sometimes, little kids, they'll put their hand up, even at home. So he goes, I want toaster strudel. I said, perfect, I'll have one too. So I put them in the thing. And they come out, I get the little packets of icing. And for once, I've actually got them separated such that I haven't just ripped the icing in half and it's all over my hand. So for once, that's happened. So then I carefully, and I got, oh, perfect. I even have the little spout. It's going to work. And I'm doing this, and it's like, it's just not working. It's really annoying. But they are quite delicious. They are quite delicious. I know that, on the plains of the savannah 200,000 years ago, had you gone up to some guy and said, you could either eat what it is you're out to hunt or have one of these. What do you think of that? He'd be like, and then humanity would have died out. They have no icing left. Then you got to make icing. And your kid's like, well, there's no icing. Oh, yeah, I'm going to make icing at 7 o'clock in the morning. Yeah, we'll put jam on it. Yeah, or just some syrup, just to sweeten it up a bit. Yeah. You can use those actually as the two sides of I did this when I was a young person like you guys. This was like one of my hangover foods. I would take 2 of those and I would toast them, and then I would put sausages in the middle and eat it like a sandwich. It's amazing I'm alive still. It really is amazing that I lived to be, pushing 50 at this point. It's okay, we got to work out. Remember they do the expected values. Expected value for like this back in the old days, we were talking about simple analysis of variance, and the expected value for mean squared treatment was basically tau plus epsilon, and the expected value for mean squared error was epsilon. And then we knew to figure it out, well, it's pretty obvious in that case, if we're going to find out if there's a treatment effect, we're going to take mean squared treatment divided by mean squared error. Yep, so let's do that for this. Oh, Why did I do that? I have it right there. Why did I just say that and write that down when it was written right here? So the expected value for simple ANOVA mean squared treatment is epsilon plus tau, and expected value for mean squared error is epsilon. So we would divide mean squared treatment, mean squared error to find out if we had an effect. Right? Yeah, so that's basically we're doing the same thing here, except now we're going to have mean squared A, mean squared B, mean squared AB, and mean squared error. Yep.
Do the two epsilons not just cancel with the same number?
Basically, yeah.
So what's the point of even adding them?
Well, no, because you got on the top, right? Which basically says that it's tau over epsilon plus 1, right?
Why one?
Because epsilon over epsilon it cancels to 1.
Then why is it also tau over epsilon?
Tau over epsilon. Like it's like if this was 3 plus 4 over 4, that's also 3 fourths plus 4 fourths. Just math.
Why do we keep the e in the bottom?
Because that's what we're dividing by.
But if they canceled out, then it wouldn't.
They don't cancel out here. They don't cancel. They don't cancel to 1 on this one, just on this part.
We get to look at t plus d or tau plus d as being in brackets.
Yes. Yes. That's right. So we have the same thing here. We got mean squared A, mean squared B, mean squared AB, and of course mean squared error. Mean squared error is going to be exactly what you expect it to be. In fact, these are all going to be what you expect them to be. Assuming you're expecting them to be anything whatsoever. But these are not going to be surprising. Expected value of mean squared A is alpha plus epsilon. Expected value of mean squared B is beta plus epsilon. The expected value of mean squared AB is alpha beta plus epsilon. The expected value of mean squared error is epsilon. Yay! So we're going to divide this by this by this, and this by this. So now we're going to do 3 f-tests to determine if there's an effective A, if there's an effective B, and if there's an interaction. So that's wonderful. That's right. That makes sense. Sure. So you're dividing all of them by mean squared error to kind of, it's not really isolating, but to isolate the effect in essence, basically to find out how much is there an effective A, is there an effective B, and is there an AB effect. Great. Yay. And the crowd goes wild. Yay. However, yeah, you thought there'd be a but, yeah, but what? Those expected values are only the case, they're only the case when you are only interested in those particular values of A and B, and no other values at all. In other words, all you care about at all are the levels 1 and 2, or high, medium, low, whatever, A, and the levels 1 and 2, whatever the hell they are, of B. You are not interested whatsoever in the levels, in anything between 1 and 2, between 2 and 3. The math only actually works if those are the only levels you're interested in. And you're going to say, what do you mean? How can the math know? Because of the theory behind this said, these are what you're interested in and nothing else. And I'll show you in a second, there's another way to look at this. And then you'll see, oh, I see why. That it's going to be different with something else. So again, you're only interested in, and think about the Tulving-Schechter and Stark experiment, right? We had 5 minutes, 1 hour, or 5 minutes, 24 hours, 7 days. That means if you draw that graph, which everybody always does, the line graph, technically you can't connect the dots. Because you don't know anything about what happened in 4 days. You can't interpret it that way. Whoa. That's bad. It's just dots. called a fixed effect model. And it's the standard one we use, by the way. It's called a fixed effects model. Okay. What if we randomly chose the levels? Randomness is always our friend in statistics. Why don't we randomly choose the models? Put all the possible levels in a hat, and we'll draw them from a hat. Okay, so we can randomly choose models. Levels, rather. So it comes out that it's 2 hours, 72 hours, and 42 seconds. That's the 3 levels we just randomly chose from a hat. Okay, that's called a random effects model. Okay, and this is where things get weird. You're going to say, why do the expected values of mean squares change? The way you calculate the mean squares doesn't change at all, but the expected values of mean squares change. And you're saying, why? Well, it's because the math behind this has to take into account the random choice of levels. Okay? Yep?
On your slides have epsilon, and in the slides I think
They might have a sigma. Yeah, I probably didn't print out the better versions where I caught the mistake I made.
So
Yeah.
there's supposed to be
Those
epsilon.
sigmas should be epsilons, yeah.
Okay.
Yep.
It's confusing me.
Yeah, they should be epsilons. They should be epsilons, not sigmas. Okay. In this case, if we randomly choose the levels of A and B, the expected value of mean squared A is alpha plus alpha beta plus epsilon. For mean squared B, it's beta plus alpha beta plus epsilon. The interaction suddenly just shows up as part of the expected value. Mean squared AB is alpha beta plus epsilon. Okay, that didn't change. And that didn't change. So how are we going to find out if there's a main effect of A? What are we going to divide mean squared A by?
A minus 1?
No. Mean squared A, it's already divided by something minus 1, right? It's a mean squared, or sum squared. What are we going to divide mean squared A by to find out if there's an effect of A? To isolate alpha.
Number AB.
Yeah, mean squared AB. Look. Hey, so what left? Yeah. What are we going to divide mean squared B by? Well, same thing. Now, mean squared AB, happily, we still divide by the mean squared error. But what we call our error term for the main effects, now is the interaction. We divide mean squared A by mean squared AB. We divide mean squared B by mean squared AB. We divide mean squared AB by mean squared error. That's for a random effects model. When we randomly choose levels, we don't do that very often, actually. In fact, I don't know that I've ever done this. There's a reason I'm telling you about this, and it will come clear in about a week. Well, more than a week, because I won't be here next week on Thursday. Yeah, I'll be in Florida. Yeah. A week from right now, I will still probably be asleep. Oh, yeah. Listen to the ocean. Waking up with a hangover going, I got to give a talk this afternoon. It's what you got to do. It's what you do. It's my job. So we divide mean squared A by and mean squared B by mean squared AB. That becomes our error term. Now, the error term for mean squared AB is still mean squared error. So it just changes. It's very rare when we do this in psychology. We use a random effects model. Now, what if we did a mixed model where A is fixed and B is random? And this is going to look ass backwards, and it's not. I'm right. Okay, A is fixed, yet the expected value is alpha plus alpha beta plus epsilon. B is beta plus epsilon, even though B is the random, and then those two are the same. So in a random effects model, a mixed model where A is fixed, what do we divide mean squared A by? By the interaction. What do we divide mean squared b by? By mean squared error. What do we divide mean squared ab by? Mean squared error. And I know that looks backwards, and it's not. Okay? It's counterintuitive, but it's... A is fixed, B is random. And like I said, I know it looks backwards. And I know it isn't. Don't you think those look backwards? So that looks like...
Yeah.
Yeah, that's the expected value for mean squared A is A alpha plus alpha beta plus epsilon. That looks a whole hell of a lot. In fact, it's exactly the same as the one for a random effect, but I said A was fixed. So it's not a typo, and I know it's counterintuitive. The typo is that maybe if you downloaded the PDFs, it'd be sigmas or epsilons. It shouldn't be sigmas, it should be epsilons. I finally made that change. Every year I'd say, I gotta remember to make that change, and I wouldn't. And I did. And it was good. I still haven't put it on the internet, though. Okay. I know this is weird, but it's the way it is. Okay? Just saying. So, we're assuming you may think, why would we always use random effects model then if we can talk about all the levels? Well, we're assuming the random effects model that we actually are randomly sampling levels, and that the levels of the randomly sampled levels are independent of each other. We never meet that assumption. Hardly ever. It's very rare. So what we do is we do a fixed effect model analysis typically. So what we typically are actually doing, like really, is a kind of sort of random fixed effect model. Kind of. But what the math we use, the expected values we use are for a fixed effect model. We almost always use that. We don't use random effects, except under a very specific circumstance that I will tell you about later next week, or the week after. All right. The question you have to ask yourself is: did you do anything remotely like randomly selecting the levels? And you never did. Not even remotely like it. You purposely got them. So like, it's different than like, you know, we always say that the subjects were randomly selected and we sort of nudge in a wink. They really weren't, but they were a lot more closely randomly selected than we actually purposely picked the people, right? So in that case, we go, yeah, we satisfied that assumption enough. We don't when we select our levels. Or exceedingly rarely do we. Okay. You get an analysis of variance summary table that looks like this. Source of variation A by B, error, and total. Now this might say, when you do like an analysis using SPSS or any other statistical program, you will get probably the name of the variable, and then you'll get name of the variable times name of the other variable, right? And then you'll get something, you can say error or say residual, something like that. So you get A minus 1 degrees of freedom, B minus 1 degrees of freedom. The sums of squares are sum of squares A over A minus 1, sum of squares B over B minus 1. There's no division there, there should be. Sum of squares AB divided by A minus 1 times B minus 1. Sum of squares error divided by AB times N minus 1. And if you're doing fixed effects, mean squared A over mean squared error, mean squared B over mean squared error, mean squared AB over mean squared error.
So once you've got novels, do you have to add them together somehow as a thing to find the F?
No, those are 3 Fs. Those 3 tests.
Oh, so
Is
you
there,
have to
is there an
find
A effect? Is there a B
separate?
effect? Yeah. Yeah, exactly. Is there an A effect? Is there a B effect? Is there an interaction? You find out if there's a difference. Right? Okay. So that's what you end up with in the end. You get the summary term. It looks a lot like the other one, except it's got these two extra terms, one more variable, and the interaction term. Right, so one more variable in the interaction term, but still, it's the same principle. It's the same principle totally. These designs can get bigger than this. I just threw in a C now. Now I got C1 and C2, A1 and A2, and B1 and B2. So now I have 6 cells. Sorry, 8. I got 2 levels of A, 2 levels of B, and 2 levels of C. So now, with a design like this, and this is not an uncommon design. This would be a 2 by 2 by 2. This is not an uncommon design. Okay, this is, I've used this kind of design many times before, for example. So now, okay, last time we were talking about factorial designs, and we were getting to a point now where we had, if you remember, we had A, B, and C, right? So now we have 3 main effects. We have a main effect potentially of A, a main effect of B, and a main effect of C. So now you have potentially 3 main effects. 3 two-way interactions, AB, AC, and BC. And the 3-way interaction, ABC. Okay? So a 3-way interaction is when a 2-way interaction, the 2-way interaction changes depending upon the level of a third variable. Okay? So it's just a general kind of rule here. So the same sort of thing, like if you had a 9-way interactions, the 8-way interactions change depending upon the level of the 9th variable. Okay? Not that anybody ever does 9-factor designs, but one could. So you could get something like, if in 1, so there's A1, there's A2, there's B1, there's B2. So first of all, if we just looked at this in isolation, this here, this is clearly an interaction, right? Because look, the effect of B2 bigger than B1 is way bigger at A2 than it is at A1. But if we said that's C1, and under C2 it looked like this. That's now a 3-way interaction. Okay. And you might think that, well, when would we get something that complicated? It's actually, if you think about it as an example, it's not that complicated. If you think of the C variable as being 2 species of birds, and then the A and B are different kinds of stimuli they remember, right? And so you can compare psychology, or you can think of the sexes, right? So you have 2 variables that change within the sexes, and you're comparing men and women. These things happen, it's not uncommon to find 3-way interaction. What if they're showing that thing next door that you can be using that subwoofer?
Would a group like that also be considered, like, say, experimental group?
You could do that, sure, it could be. Yeah, so you could have a, could be experimental.
Different levels of it?
Yeah. I mean, the idea is that having a couple of groups and then 2 more variables to also divide them up is not something that's uncommon. 3-way interactions you see all the time. 4-way interactions get exceedingly complicated. Also, I can't think in 4 dimensions. Like, I have trouble breaking things down that way. I don't let my honor students do anything more than usually 2, sometimes 3. I one day let a guy do a 4. He's actually worked back in Newfoundland. He's a postdoc at Queen's doing neuroscience now. He's, and that doesn't mean anything. All I'm saying is that's one guy. That's one guy. And the whole time I've advised honor students. I can't think that way. I can imagine this. See, because if it was a 4-way, then that would be D1 and then D2. It'd be a different path. And it's hard to even think of an example. I could give you tons of examples here. My whole freaking PhD thesis was like that. It was all 3-way interactions, all about species differences and 2 different kinds of stimuli. And then retention interval. No problem. So that's not uncommon. And to those of you listening to the audio, the person in the next classroom is, I don't know, watching Top Gun or something. A lot of bottom end. All right, does that make sense? Okay. So the model for this, for a three-way, is x equals mu plus alpha plus beta plus gamma plus alpha beta plus beta gamma plus alpha gamma plus alpha beta gamma plus epsilon. Okay. You made the plus epsilon doesn't show up on the screen, of course, as usual. It's a gamma. It looks like it's a small Greek gamma. Okay. Yeah, it's not annoying at all. It'd be like a Barry White meets the adults on like Charlie Brown.
Yeah.
Which just seems wrong on so many freaking levels. I doubt it. I could yell right here. We'll go next door and say, "Turn that shit down." That's not very respectful. They're doing something there. Clearly, it's pedagogically important to watch something with that much bottom end. No, in evolutionary psychology, we sat here and we watched Walking with Cavemen for 2 days. I don't think it was that loud, but it might have been. Difference is, I'm sure that it was more interesting than whatever that is. I don't know what it is. I don't even know what that class is. And I don't care. Okay. So you see the model there? I mean, now look, you could make it 4, and it would be, x equals mu plus alpha plus beta plus gamma plus delta plus alpha beta, alpha gamma, alpha delta, beta gamma. Yeah, and then gamma delta, and then we would go alpha beta, alpha gamma, alpha beta. It would get long. And like I said, no one usually uses 4-way designs anyway. It's crazy. Like I have seen one where a student of mine did, and I can think of one example. A prof that taught me this stuff at Western in third year. He had some stuff. He showed us a 4-way interaction. But like he said this is something that he doesn't even like because it's hard to think in 4 dimensions. So it might look like this. This is sort of what I drew up here. So you can see that the effect, this is C1 and C2. So we just have 2 different patterns, 2 different 2-way interaction patterns. That's all. That's all that is. It's nothing to be, and again, when you think about something like comparative psychology or doing sex differences, this isn't going to be a surprising thing that these kind of patterns show up. Okay? So same sort of ideas what I drew up on the board. All right. No, they didn't hear me because there it goes again. I don't blame them so much as the people that didn't put any insulation in the walls. So, questions about that? So, like I said, sort of what I drew up here. Same idea. Okay, now these designs have some great advantages and disadvantages, and we'll often talk about these kind of things. We can study interactions. That's a big advantage because many of our theories in the life sciences in general, psychology in particular, have interactions in them. We say that you look at all the stuff in memory. A lot of you guys are taking a memory class with me. We look at how different variables affect different kinds of memory. So, episodic memory decays at a different rate than semantic memory, things like that. You look at implicit and explicit memory, how one decays, one doesn't, or how one is affected by levels of processing, one isn't. So all these kind of things where a lot of the theories we have in psychology, and really biological sciences in general, have interactions in them. So to be able to study them, that's wonderful. relatively simple to interpret once you've done it a couple of times. Once you've looked at it, you know what an interaction means, you know what a main effect means, it's really not that hard to do. You can look at something and say, well, yeah, sure, I can flash labeled now, I can take a look and see why we would get these different patterns in different groups. So they're really pretty simple to interpret, especially compared to some of the other designs we're going to talk about. Now there's a downside to these things. Now the question is, remember we talked about fixed and random models. Is it a fixed model, a mixed model, a random model? Well, usually it's fixed. We just assume it's fixed and go from there. These things can get very big very fast. So, now you don't have to write this bit down, but I'm just going to show you how big these things can get. So, if we have A and B and A by B, that's not bad. And then we bring in C, and now we have the two-way interactions, C, A, C, B, and B, and A, B, yep. And then three-way. That's not so bad. Now remember, that is 1, 2, 3, 4, 5, 6. That's 7 F tests, but you know, software don't do that, right? So big deal. Now we bring in D. That's right. DA, B, D by A by B, by C, D by C by A, B by C by B, and A, B, C, D. As you can see, by the way, if we brought in a fifth variable, this is going to double in size. That's a lot of effects. Yep.
You said a three-way interaction is 7 F tests?
Well, for the three-way, there's the one test, the A, B, C. But there are 7 to do, right? Because just up to here, 1, 2, 3, 4, 5, 6, 7. You're going to test the F for A, the F for B, the F for AB, the F for C, the F for AC, the F for BC, and the F for ABC. Right? And now put E on, or D on there, and now suddenly you've got 14 to do. You put E on there, you got 28 Fs. This is very big. And now think about suddenly, if you do this, and you want to say have 20 subjects per group, 24, 265, 560 people. Yeah. So it's not a good idea. Right? It's going to be a nightmare. Right? And you double that, you're 1,020 people. That's ridiculous. Right? So these things can get very big very fast. That's the concern. All right.
So if you want